Yes, and first of all, let's consider again and this and the problem 3, and the page number this one. It's okay. Uh, Question this one from our book, and ty double prime minus 1 plus ty prime plus y is t square e to the 2t, t square this one. It's okay. There's yes, and this one right hand side should be t square e to the 3t, t greater than 0. And the question, verify that y sub 1, y sub 2 are solutions of the given equation. Find and also find the particular solution. It's okay. And y sub 1 and y sub 2 we have, and y sub 1 and y sub 2, and check that and these solutions and these and the function solutions of the given equation. It's okay. Differential equation and fundamental solutions, we claim that, and also find the particular solution. Yes, take our differential equation. It's okay. Non-homogeneous equation, second order, and also linear differential equation. It's okay. And t greater than 0. But and look at this one, not standard form. Standard form means and our differential equation. Look at our differential equation. Coefficient of y double prime should be 1, but here not 1. So and to get the coefficient of y double prime 1 here, how to get, and they multiply 1 over t greater than 0, and means t is not 0, so this one is not defined, and it is possible to multiply by 1 over t, and then multiply and our equation, and we obtain standard form of our equation. It's okay. So our equation here, standard in the standard form, this one. It's okay. So and the first part, and check that this function 1 plus t and e to the t solutions of our equation. It's okay. And so this one is homework. It's okay. It is easy to see that, and because take the y sub 1 plus t, compute prime 1, y double prime 0. So and take this one, substitute here. So this one is 0. This one is 1. 1. So and this one is 1 plus t. It's okay. And they check that, but of course, and it should be, and we claim that this one and this one fundamental solutions of the homogeneous part. So our differential equation here and this one, first of all, take the corresponding homogeneous, and we claim that y sub 1 is a solution. Solution means substitute here, and then we obtain 0. So and minus 1 plus t plus 1 plus t, and we obtain 0. Yes. So we can say that y sub 1 is a solution. It's okay. So and take the other solution, y sub 2. Now let's see that y sub 2 is a solution of our differential equation. Compute the prime first, e to the t, and double prime the same, and substitute here. This one satisfies our homogeneous equation. Yes. T times e to the t minus 1 plus t e to the t plus e to the t, and check that this one is 0 or not, and t e to the t minus, yes, and also minus e to the t plus e to the t, and we obtain 0, 0. Yes, y sub 2 is a solution of our differential equation. It's okay. So next part, and find the particular solution. Find the particular solution. If and we have two fundamental solution of the homogeneous equation, it is easy to get the particular form, form of the particular solution. And also, but be careful, and the y sub 1 and y sub 2 solutions, but you have to check that fundamental solution or not. Otherwise, it is not possible, right? general solution of the R homogeneous, the general solution of the corresponding homogeneous differential equation, because y sub 1 and y sub 2 are and should be linearly independent. And so you have to compute the Ronskin determinant first. It's okay. So, and the homework, this and the compute this determinant, and it is easy to see that this one is not zero. So, and means y sub 1 and y sub 2 are fundamental solutions. It's okay. Solutions. This part homework is okay. So, yes. We can write the general solution. General solution C1 y sub 1 plus C2 y sub 2. And so we obtain the general solution of the homogeneous equation. Yes. Now, the second part of our question, find the particular solution. Yes, now we can write the particular solution of the non-homogeneous equation. This one. It's okay. So we know that, and the substitute C1 U1 is okay, and the write the U1 instead of the C1 and U2. And this one is, we claim that this one is particulars. Our aim is to find the y sub p under this assumption we know that assumption and u1 prime y sub 1 plus u2 prime y sub 2 prime is 0, and also other equation u1 prime y sub 1 prime u2 prime, and take the derivative of y sub 2 prime should be g of t. It's okay. So u1 prime y sub 1 u2 prime y sub 2 is 0. Yes, this one. And write this one. It's okay. Second one. So u1 y sub 1 prime and take the derivative with respect to t, and this one is 1. Take the derivative with respect to t, the same, e to the t, should be g of t. G of t, this one. It's okay. So, and our aim is to find here u1 prime and u2 prime. It's okay. So use elimination or Cramer rules. It's okay. And then we obtain u1 prime and u2 prime. And here we know, and we get two equation to get the linear system, and this linear system contains two unknown. First unknown u1 prime, u2 prime, and also this system has two equations. Okay, so use the Cramer's rule. Write the coefficient matrix. Yes, coefficient matrix is noted by here the delta, this one. So this one. So compute to this one, so we obtain t e to the t not 0. It's okay. And also we know that, and here you homework parts, and compute the Wronskian y sub 1 and y sub 2, and this one is y sub 1, y sub 2, y sub 1 prime, y sub 2 prime. And also this one is the coefficient matrix of and the delta. It's okay. Coefficient matrix of the system is delta denoted by, and also this one is Wronskian determinant, and here not 0. Yes, and this one, and also fundamental. It's okay. Again, we see that, and it is solutions fundamental solutions. This one is non-zero because and the t greater than 0. And the exponential function non-zero, and also t non-zero. So, and the product does 0. It's okay. So, and the compute the first unknown u1 prime, delta u1 prime over delta. So, and the 1 over t e to the t, and the right side will be first column, the second column the same. It's okay. Stays the same. And then we obtain and this one. And compute that u2 u2 prime is okay, and the delta this one coefficient matrix, and the second column will be right hand side, and the first column stays the same. It's okay. And then we obtain u2 prime this one, u1 prime this one, u2 prime this one. So take the u1 prime and integrating both sides, so we obtain u1 is this one. It's okay. And u2 integrating both sides and take the u2 prime and here. It's okay. So we obtain an product and here, and you have to use the integration by parts here, integration by parts, and this product is the product of the polynomial and exponential function. Of course, u should be 1 plus t, and dv is this part. Is okay. So du is dt, and integrating both sides, and we obtain v. It's okay. And use the formula integration by parts, and we obtain u2. u2 is this one, u2 this one, and also u1 minus 1 over 2 e to the 2t, and write the particular solution. We know that particular solution is u1 y sub 1 plus u2 y sub 2. u1 this one, y sub 1 this one, and u2 this one is y sub 2, this one is y sub 1. So rewrite, and then we obtain this one. It's okay. We obtain our solution here. It's okay. Any question about the solution? Yes, let's come back here. It's okay. We know and from the last lecture, and this one is the differential equation and order linear equation. It's okay. And a non-homogeneous g of t, and the L is a linear operator, L of y is 1. It's okay. So, and the corresponding homogeneous equation L of y is 0, and the order n, and so, and y sub 1, y sub 2, y sub n are fundamental solutions of the homogeneous equation. And we claim that, and if we have the n fundamental solutions, or and the solutions only, it's okay, solutions of the homogeneous part. So we know that, and take the linear combination of these solutions, also solution. And so write the we know that if L of y is 0, write in here y sub I 0, and y sub I is a solution. So we claim that take the and solutions of our differential equation, take the linear combination of these solution, also solution of the homogeneous, the corresponding homogeneous differential equation, and here C1, C2, Cn constant. It's okay, constant. So we know, and this one, and from and previous lectures is okay, because, and we know that, and this in the theory, and for second order linear differential equation, and also, and these rules and in theory, and also are valid, and for the differential equation of order n. It's okay. So, and how to check that, and there are solutions, fundamental solutions of the homogeneous and equation, if and only if compute the Wronski indeterminate. Wronski indeterminate should be non-zero. It's okay. And so what is the determinant here? And the first row are solutions. Second row, derivative of the first row, and the next row, derivative of the second row, and then the last row will be, and solutions of the and the derivative and again and again take and the n-1 it's okay. So we obtain this one is Wronskian determinant of the n solutions, and our determinant should be n by n. And look at this one, our determinant contains n row, it's okay, and also n column. Yes, n by n determinant, it's okay. So how to check that our solution is fundamental? Compute the Wronskian determinant should be non-zero. Yes. If non-zero, and so fundamental solution, so we can write the general solution of the homogeneous part, y sub h, c1 y sub 1 plus c2 y sub 2 plus cn y sub n. It's okay? Is the general solution of the corresponding equation. Yes. Now, and we know and from the previous lecture, and this one and this one linearly independent. So this one is linearly dependent. Coefficient C1 minus 4, 1 and 1. And we know from the previous lecture. And yes, let's look at the next one, next question. And the question here, verify that the given functions are solutions of our differential equation and determine Wronskian determinant. It's okay? Wronskian. So, and our differential equation this one, y sub 1, 1, y sub 2, t, and the next solution e to the minus t, t e to the minus t. We claim that these functions are solutions of the differential equation. And first part, and they check that this one is true or not. And then compute the Wronskian. It's okay. So, and let's first of all, let's check that, and the y sub 1, 1 is a solution of the our differential equation. So how to check that? And this one is solutions of our differential equation. Substitute here to check that this one gives 0 or not. It's okay. So y sub 1 is 1. It's okay. Y sub 1 is 1. Sorry. And y sub 1 prime 0. And next, take the derivative again and again. And then we obtain all of them 0. It's okay. So, and this one is 0 or not, our differential equation, this one. So substitute here y sub 1, y sub 1, y sub 1 to check that this one is 0 or not. So y sub 1, 1, and the derivatives of all derivatives 0. So right here, it's okay. There is no y sub 1 here, so all of them 0. So we obtain 0. Yes, means y sub 1, 1 is a solution of our differential equation. Yes. The next one, the second function is the second solution of our differential equation. So compute the derivative. It's okay. So substitute y sub 2 is t and all derivative and in our equation. So we obtain 0. Yes, means t is a solution of our differential equation. And similarly, and check that e to the minus t, e to the minus t, take the derivative of all of them. It's okay. And substitute here. And then we obtain 0. So this one is a solution. And also, and compute all of them. And then this one is a solution. It's okay. So yes, y sub 1, y sub 2, and y sub 3, and y sub 4 is are solutions of our differential equation. Yes, our differential equation order here 4. Yes, we have four solutions. It's okay. So how to write the general solution, but it is not enough to say that and these functions are solution. You have to check that these functions, these solutions, fundamental or not, you have to compute the Wronskian. It's okay. There's a typo, not 2 here. And this one, Wronskian should be, and this one. It's okay. So if we get this one non-zero, so fundamental, fundamental, so we can write the general solution. C1, y sub 1, y sub 1 is 1, y sub 2, y sub 3, and y sub 4. It's okay? So, now, but first of all, you have to compute the Wronskian determinant and then we will write and the general solution. And Wronskian determinant, this one, write the first row, y sub 1, y sub 2, and y sub 2, y sub 3, and y sub 4. The second row will be derivative of the first row, 0, derivative of the with respect to t1, derivative of the e to the minus t minus e to the minus t, and this one is product rule. Use the product rule here, the last entry for last entry, and derivative of the first one, 1 times second one, and plus first one times derivative of the second one, and e to the minus t minus. So we obtain this one. It's okay? Yes. And then take the derivative with respect to t again to get the next row, this one, 0, 0, minus and minus, plus e to this one, and this one, use the product rule, and the first one, yes, derivative of the first one, minus 1 times the second one, plus first one, derivative of the second one, e to the minus t minus. It's okay? So, we obtain, yes, here we obtain, and this row is okay, this one, and then this one is true or not, and we take this one and the derivative, and the first part, derivative of the first part, minus 1 times e to the minus t plus, and the first one, 1 minus t, derivative of the second one, e to the minus t minus 1, and then so it's not true, maybe. There's a problem here, maybe. Any idea? And I take the derivative of this one, 1 times e to the minus t, and plus t, e to the minus t minus. So we obtain 1 minus t, e to the minus t. This one. Yes, it's true. And I take the derivative again, and with respect to t, minus 1 times e to the minus t plus 1 minus t, and take the derivative this one, minus e to the minus t, and minus e to the minus t, minus e to the minus t, minus and minus plus t e to the minus t, and this one, yes, minus 2 plus t e to the minus t. There's this one, it's not true. It's okay. This one, it's not true. So you compute and this one. It's okay. This one, there's a problem here. Yes, this one is not true. It's okay. This one is not true. So compute and the next one. This one is not true. It's okay. But we know that, and this one is non-zero. This one is non-zero, and so how to compute and this determinant expansion, and then we obtain 3 by 3 and use the first column expansion, and also we obtain 2 by 2 determinant, but we know that always our and the entry contains e to the minus t and e to the minus t, and here also this one is e to the minus t and this one gives e to the minus t. So we obtain this one is true, this part, but this part maybe, and check this part, maybe true, maybe not, because this one is not t minus 1. This one should be minus 2 and plus t, and again compute to this one different. So compute this determinant. This determinant is the here and the non-zero, because what's the reason? And this one contains maybe, and this one is exponential. So homework, compute to this one. It is easy to see that. It's okay. This one is non-zero, so fundamental solutions. It's okay. So we can obtain the general solution of homogeneous part. Yes. It's okay. But and the Wronskian determinant, this one is the coefficient maybe, and the e to the minus 2t is okay. Yes. There's a typo here. It's okay. And this one is not true. This one is not true. It's okay. So now here, what can you say about the non-homogeneous linear equation of order n? It's okay. Y sub capital Y sub 1 and Y sub 2 are solutions of the non-homogeneous linear equation of the and this one. Non-homogeneous because and here g of t is okay, non-zero. If we know the and Y sub 1 and Y sub 2, sorry, solutions of the non-homogeneous equation, and means satisfy our differential equation, we claim that, and also look at the Y sub 1 minus Y sub 2, also solution of the homogeneous part, and also we obtain the solution of the homogeneous part. And if this one is a solution of the non-homogeneous equation, and the second one, and also non-homogeneous solution of the non-homogeneous equation, and compute and this one, it is easy to see that L of and the y1 and y sub 2 is, we know that L is a linear operator, and we can write the L of y sub 1, L of y sub 2, and we know that L of y sub 1 solutions of the non-homogeneous equation, and this one is g of t, and also y sub 2 is a solution of the non-homogeneous linear equation, and so this one is g of t, so we obtain 0. So we obtain 0, and means and L of y sub 1 minus y sub 2 is a 0, and means and this one is a solution of the homogeneous equation. It's okay, the corresponding homogeneous equation. And consider the non-homogeneous equation here. It's okay here, and so we claim that the general solution of the non-homogeneous equation has this form. It's okay. Has this and the particular solution. Sum of the consider the non-homogeneous equation. It's okay. The general solution of the non-homogeneous, the given equation, should be in this form. What's the form? And the sum of the general solution and plus particular solution. And here y sub h, the general solution of the homogeneous part, and the y sub p, particular solution of the non-homogeneous equation. Same. It's okay. So, and then now, if our homogeneous equation of order n with constant coefficients, look at this one. L of y is 0. It's okay. Homogeneous equation, and also and the linear differential equation, and also look at the coefficient of derivative and y, and constant here. It's okay. an minus 1, a sub 0 are constant. So our differential equation, homogeneous differential equation of order n and with constant coefficients. It's okay. A linear differential equation, of course. It's okay. So, and here, and we know that, and we claim that e to the rt, if e to the rt is a solution of our differential equation, and means, and substitute here, and this one gives 0. And substitute here, we obtain this one. But this one should be 0. It's okay. And e to the rt non-zero, every r is okay. And so this part should be 0. If this part should be 0, so we obtain 0. Our aim is to get and e to the rt. If e to the rt is a solution, what is the r here? Have to get r. It's okay. So this one is a solution and means this product should be 0. This product should be 0 means, and this one should be 0. First part should be 0 because second part non-zero. It's okay. So, and the first part is 0, and this one we know that, and this one from the second order linear differential equation, this one with constant coefficient, this one is called characteristic equation. Yes. And here, and this one is called characteristic equation. So characteristic equation contains n roots. It's okay. N roots. So we obtain n roots. So, and write the here, and so e to the rt, we obtain n solution. It's okay. So our differential equation of order n. So our aim is to get the n fundamental solution. It's okay. Fundamental solution. Yes. Let's give an example. It's okay. And the first one, find the solution of the initial value problem. The following initial value problem. Initial value problem means our problem contains one differential equation. Look at the order. Order is 4. It's okay. So every initial, and also we know that every initial value problem has a unique solution. But to get unique solution, we have to get 4 here for initial condition. But we have 4 initial condition. Yes, this one is the initial value problem. So our aim is to get the unique solution of this and the initial value problem. It's okay. So first step, step 1, find the general solution of the differential equation. This one. It's okay. Solve this and the differential equation. How to solve? And the first one, this one is homogeneous and the linear, and coefficient. Look at coefficients 1, 1, minus 7, minus 1, 6, and constant coefficients. So how to solve this differential equation? Write the corresponding characteristic equation. It's okay. So, and characteristic equation here, yes. R to the 4, R cube, minus 4, R square, minus R, plus 6 is 0. Yes. And then our aim is to get the roots of this equation, characteristic equation. And so, for example, write the R is 1 here. Write R is 1. So 1 plus 1 minus 7 minus 1 plus 6. Check that is 0 or not. It's okay. So we obtain this one is 0. Yes. R is 1 means R is 1 is a root of the this and the equation. So, and using the division algorithm, and then divide the R minus 1 right here, R to the 4 and this one, we obtain other part. So, and they check that R is minus 1 also is a solution. So we obtain r minus 1, r plus 1. This one is equal r square minus 1 is a factor of under this equation. It's okay. Under this polynomial. It's okay. So, and using the division algorithm and take this one, divide by r square minus 1. So we obtain r square plus r minus 6, the other factor. It's okay. So we obtain all the roots. It's okay. R1 is 1, R2 is minus 1, and this one gives minus 3 and 2. It's okay. So we obtain y sub 1 e to the t. Y sub 2 minus 1 gives y sub 2 e to the minus t. Minus 3 e to the minus 3t. 2 e to the 2t. This one is the general solution of the R differential equation. It's okay. Any question about this part? Okay, no question. Everything is clear. And the next step, this one is the general solution of the homogeneous equation, but our aim find the solution of the initial value problem. So, and means this one gives infinitely many solutions of the R differential equation. But they choose, we obtain the infinitely many solution of the R differential equation, but choose one of them. For example, this one, it's okay. This one, we get only one solution, unique solution, but this solution, and check that, and if and these initial condition and R this and the solution satisfy our initial conditions. It's okay. And choose and this one. How to get and take this one, but solutions satisfy our initial conditions. It's okay. Initial conditions. So, and the y0 should be 1, y prime 0, 0, y double prime minus 2, and this one should be minus 1. And take this one. It's okay. Y0 is 1. And take the first initial condition. First initial condition, y0 is 1, and means t is 0, y is 1. Substitute here, and then we obtain, yes, y. Y is 1, t is 0. 0, 0, 0, 0. So we obtain this one. So we obtain C1 plus C2 plus C3, C4 is 1. It's okay. First initial condition gives this equation. And then next in the initial condition, this one, y prime 0 should be 0. And the y is this one. What's the y prime? You have to compute to y prime. Y is this one, y prime. Take the derivative with respect to t, c1 e to the t, and this one gives minus c2 e to this one, and the derivative of this one minus 3 times c3, and this one gives the last term. So y prime this one, but you have to compute the derivative with respect to t because the next initial condition y double prime. And this one, take the derivative with respect to t for the last initial condition. So you let's compute all derivative here, and y double prime and y and this one. It's okay. We obtain this one and this one and this one. So write the initial condition. Y0 is 1. We obtain this differential these equations. Sorry, this one. So and the y prime 0, the second initial condition. Take this equality and substitute t is 0, y is 0, so we obtain this one. And the next condition, this one, take the second derivative and this one, it's okay, and substitute here. And then the next initial condition is okay. This one. So take this equality and substitute t is 0, t is 0, y is minus 1 because this one. So we obtain these equations. So we obtain 4 equations and 4 unknowns, C1, C2, C3, C4. Because our aim is to get here, this one is general solution. Our aim is to get C1, C2, C3, C4. It's okay? And how to get this one if our solution satisfies the initial conditions. It's okay. So we obtain one and this system is okay. This system has 4 equations for unknown. You have to know and have to solve this one. Write the coefficient matrix of the C1, C2, and C3, C4. Write coefficient augmented matrix solve, and using the elementary row operation we get the solution. It's okay. Solution. First of all, right here augmented matrix is okay. Look at the system. Sorry. Write the augmented matrix, this one, and using the sum elementary row operation to get the reduce, or I think it is enough here, row echelon form. To get leading one, we have leading one here, of course. It's okay here. So to get 0, 0, 0, how to get? Multiply minus 1, add to the corresponding rows. It's okay. So we obtain this one. And the next step to get 1 here is okay. And also to get 0 here. And first of all, to get 0, it will be better because minus 2, and so multiply minus 1, add to the last row, so we obtain 0. And then to get 1 here, multiply minus 1 over 2. It's okay. So to get 1 here, multiply 1 over 8. And so apply the sum elementary row operation. We obtain this form. It is enough because the sum gives C4. It's okay. So using the back substitution here, the previous and the row give C3, and substitute here C4 and C3, and then we obtain all value of C1, C2, C3, and substitute in the general solution here C1, the value of C2, value of C3, this one, C4. It's okay. So this one is the solution of the initial value problem. Yes, we get unique solution. It's okay. Any question? No question. Okay. Let's stop here. Let's have a break, 10 minutes, and then